Welcome to this explainer. Today we're taking a deep dive into the rigorous and honestly fascinating engineering life cycle of autonomous aircraft. We aren't just talking about theory here. We're going to map out exactly how an aircraft goes from a set of abstract mathematical requirements to a physical machine flying in the sky. To do this, we're using the NASA-sponsored Odyssey UAV, which was developed at Cal State LA's Space Center, as our prime example. Okay, let's dive into this. Picture the Odyssey UAV. It's a real-world, twin-boom pusher aircraft. Now, throughout this explainer, we're going to explore some highly advanced computational and aerodynamic concepts, but I want you to keep the physical reality of this aircraft in your mind. Every piece of software analysis, every high-tech fiber optic cable, and every structural trade-off we discuss ultimately results in this tangible, flying machine resting right here on the tarmac. Here is our flight plan for today. First, the Odyssey UAV mission. Second, aerodynamics and physical design. Third, virtual proving grounds. And fourth, the fiber optic nervous system. Section 1, the Odyssey UAV mission. Before a single piece of carbon fiber is even laid down, the design team needs to define the exact problems this aircraft is required to solve. So here's the mission briefing. The Odyssey was designed as a multi-mission platform with some very specific demands. It needs 3 hours of continuous flight endurance, a 10,000-foot maximum altitude, and a cruise speed of 81.4 feet per second. But the real engineering challenge? It's that 14-pound maximum payload. In aircraft design, endurance capabilities are always a direct trade-off with payload weight. Carrying heavy 14-pound forward-facing cameras while staying airborne for 3 hours, well, that dictates absolutely everything else about this aircraft's size and power. And because of those demanding mission parameters, the aircraft needs to be tough. The designers calculated that the maximum acceleration loading condition this aircraft will ever face in its flight envelope is 3.0 G. To ensure safety, they designed it to withstand that 3.0 G load with a factor of safety of 2.0. Factoring in this robust structural requirement right alongside the payload and fuel, they established an estimated gross weight for the entire structure of 140 pounds. Section 2, aerodynamics and physical design. Now we enter phase 2, where engineers translate those abstract requirements into a physical shape. And this brilliantly illustrates the traditional step-by-step progression engineers use to model an aircraft. First, you select your airfoils and general configuration. Second, you analyze that geometry to estimate lift, drag, and static margins. Third, you bring in computational fluid dynamics, or CFD, to model the airflow digitally. And finally, you validate your choices against actual flight data. Every single choice made in these steps refines the design, narrows down the performance capabilities, and directly reveals what manufacturing techniques will ultimately cost. One of the biggest choices in Step 1 is a classic aviation trade-off: stability versus maneuverability. As an aircraft's static margin increases, it becomes more stable, sure, but less maneuverable. For the Odyssey, the designers intentionally chose a 15% static margin. Why? Because they prioritized longitudinal stability. This ensures incredibly smooth autonomous flight, which is absolutely vital so the forward-facing camera payload can capture undisturbed imaging. To actually achieve that stable flight, they selected very specific shapes for the wings. They went with an Epler 214 airfoil for the 15-foot rectangular main wing and a NACA 0012 airfoil for the tail. Now, these aren't random selections. This exact combination was explicitly chosen to generate high lift at relatively low cruising speeds while providing adequate moments for a perfectly stable pitch. Section 3, virtual proving grounds. With the physical shape defined, it's time to test it out in the digital realm. Before building an expensive physical prototype, the team used Athena Vortex Lattice, or AVL software. Think of this as a virtual wind tunnel. It proved that to optimize the lift-to-drag ratio while cruising, the main wing and tail needed a precise 2-degree incidence angle. It also allowed them to simulate engine performance. Actually, instead of building a heavy, custom jet engine, the simulation proved that an efficient, off-the-shelf Desert Aircraft DA-120 piston engine could perfectly handle the endurance requirements, saving massive amounts of time and money. Now, what's really interesting about this visualization is exactly what it shows us when the airframe is under load. On one side, we see the stress contours, where the red and purple areas show that the greatest stress concentration naturally occurs right at the root of the wing, where it attaches to the fuselage. But on the other side, we see the strain contours. This shows how the physical carbon fiber composite material actually bends and stretches along the wingspan. Because the spar uses unidirectional carbon fiber, understanding this exact strain pattern is crucial for laying down the material correctly during manufacturing. Let's see how this builds into real-world predictions. By throwing these models into Nastran finite element analysis software, the engineers pushed the virtual plane to its absolute limits. They found that under that crushing 3.0 G, 720-pound maximum aerodynamic load we talked about earlier, the wingtips will deflect or bend upward by a maximum of 1.69 inches. Knowing this exact tolerance is what prevents the wings from literally snapping in midair. So, the absolutely crucial point here is making sure those bending wings don't vibrate out of control. This specific number, 8.25 Hz, is the Odyssey's first structural bending mode frequency. If an aircraft's natural frequency matches the aerodynamic forces hitting it, you get uncontrolled vibrations, otherwise known as flutter. And flutter leads directly to catastrophic in-flight breakups. Knowing this 8.25 Hz limit allows the control systems to actively avoid dangerous flight regimes. Section 4. The fiber optic nervous system. But what if the aircraft could feel those vibrations and strains itself? Traditional sensors like strain gauges are heavy, they're bulky. The Odyssey replaces them with thousands of microscopic etchings called fiber Bragg gratings, embedded directly inside hair-thin fiber optic cables. As the wing bends, the cable stretches. This stretching actually changes the physical spacing of the microscopic etchings, which alters the wavelength of the light reflecting back through the cable. By measuring the shift in the color of the light, the system instantly knows exactly how much strain the wing is experiencing. To physically map this out on the structure, engineers route lines of these fiber sensors straight across the span of the wing to capture bending strain. But notice the 45-degree diagonal placement? Those are placed strategically to capture twisting or torsion. It acts exactly like a biological nervous system, running continuously through the aircraft, transmitting pressure and pain directly to the central computer. And here is where the magic happens. All of that shifting light data is fed into an algorithm developed by NASA Dryden called displacement transfer functions. This algorithm mathematically translates thousands of individual strain readings into a perfectly accurate, real-time 3D digital model of exactly how the wing is bending and deforming while in flight. It doesn't just record data. It predicts dangerous aerodynamic flutter before it happens, allowing the onboard computer to reconfigure its flight controls on the fly to save the aircraft. It's just an incredible progression, right? From basic mathematical mission requirements to a living, feeling machine. Integrating a fiber optic nervous system doesn't just prevent immediate structural failures and save weight, it fundamentally changes how aircraft operate. It leaves us with a truly provocative question. As UAVs like the Odyssey gain the ability to instantly feel and digitally map their own structural damage in real time, how long will it be until they possess the systems to autonomously repair or structurally reconfigure themselves in midair? We are looking at the dawn of a self-healing aerospace future. Thank you for joining me for this explainer, and keep your eyes on the skies.